everyone. My name is Anita Carleton, and I'd like to welcome you to Day 3 of the CMU SEI Research Review. I've really been looking forward to this session for some time now. Today's showcase session nicely builds on the momentum of a study that the SEI currently has underway called the National Agenda for Software Engineering, focused on looking at the future of software engineering research and development. I'm really excited to chair this research review showcase on software engineering's grand challenges, voices from visionaries. Next chart. So as a brief introduction, I'm the director of the Software Solutions Division. I lead the software engineering research, development, and transition portfolio for the SEI with the specific goal of making software a strategic advantage for the Department of Defense. Next. So as a brief introduction, to just set the context for this session, software is essential to our modern life and controls functions as diverse as the capabilities for our home appliances, aircraft flight control systems, mobile phones, healthcare systems, financial transactions, and digital learning, to name a few of the areas. Individuals, organizations, markets, and governments are increasingly dependent on software. Given the ever-growing dependence on software-reliant systems, an imperative exists to maintain and strengthen our leadership and strategic advantage in software engineering. While certainly applicable to systems operating and evolving today, software engineering leadership is especially critical for future systems that will provide greater capabilities, be more data intensive and interconnected, increasingly utilize AI and autonomy, require larger scale integration, and be increasingly edge driven. To that end, we are incredibly fortunate to have the opportunity to hear from a number of visionaries today. Senior thought leaders who will briefly describe how they see software engineering enabling our visions for the future and the major open problems and grand challenges that software engineering should address to enable our visions for the future. Next chart, please. So in this showcase, experts from industry, government, and research labs will discuss software engineering's grand challenges as they relate to their respective fields of work, including nuclear science, university research, defense R&D, supercomputing, AI, tech, and thinking about future battle systems. And now, please let me briefly introduce the speakers. First, Dr. Deb Franke, the Associate Laboratory Director for National Security Sciences at Oak Ridge National Laboratory. Dr. Michael Quaid, he is the Vice President for Research at CMU. Mr. Vince Cerf, Vice President and Chief Internet Evangelist for Google. Vint, I love that title. Mr. Alan Dynec in place of Mr. Tim Dare, and Deputy Director for Prototyping and Software, Office of the Undersecretary of Defense for Research and Engineering. Ms. Sarah Manning Dawson, the General Manager for Microsoft Critical Infrastructure Engineering. Dr. Bill Shurlis, Director of the DARPA Information Innovation Office. And Mr. Nan Mulch, the CTO of the Joint Artificial Intelligence Center. Okay, next chart, please. So here's the game plan that we have. I've prepared a specific question for each of the visionaries. After I read the question, each speaker will have roughly 4.5 minutes to provide their thoughts, and then we'll move to the next speaker and question and so on till we get to Nan, who will be our closing speaker. After that, we'll be excited to take questions from the attendees. So please, as you're listening to all the speakers, be thinking about what you'd like to ask each of the visionaries. Okay, chart 7, please. So with that, let's kick things off with Dr. Deb Franke. So So at Oak Ridge, I'm sure you faced many grand challenges related to your areas of focus of advanced materials in manufacturing, supercomputing, and nuclear science. Hopefully, software engineering has been an enabler to meeting those challenges. How can software engineering enable or accelerate progress in one or any of your grand challenge areas?
Anita, thank you so much for that question. And I'm going to use up some of my precious 4.5 minutes to thank you so much for pulling together this panel. You've got a lot of really great people who are friends and colleagues on the line, and I'm motivated to get done within my time slot so I can hear from them. I love that question for a second reason. I spent most of the last 9 years at the National Security Agency dealing with defense, intelligence, support of the nation's systems, and it's been really an interesting pivot to step back and look at software from the context of what we do in science. And so I've geared my response mainly towards that piece. So what's been interesting for those of you who may not have looked at big science in a while is that you're mainly aware that big science relies very heavily on what one does with the big iron, the high performance computing. Really critical investments in new approaches are equally important. And the algorithms and the data are part of it too. What was a little startling to me is how integral the algorithms and the software itself have become to the scientific process. Because at the time I last worked in the National Lab system, primarily we hired people to write software for relatively well understood algorithms and have them run effectively on the large scale systems. The game has now changed. So for instance, I'm investing in a really cool program that's intended to support a future challenge, future nuclear reactors. They will be smaller, they'll be made and use different processes. And in order for this to be effective and to meet some of the mission needs we have on the non-proliferation side, we need to be able to distinguish amongst two different kinds of isotopes of plutonium. So bottom line question, interesting problem. You would think that that had a lot to do with lab work, and it does. But this particular investment I'm making is really more about how do we properly implement the kind of machine learning tools that will take the data that we'll gather and rally that around a solution. And that's an interesting example because what it shows you is that the software is now an integral part of science in that it's not just enough to have instruments that have sensitive detection capabilities and not enough to have horsepower, but you've got to have software. Now, software isn't a lump of code that sits in one place that we can look at anymore either. Software is what comes together in the environment in the moment. So the software in my field, particularly in science, has to do as much with what are the actual elements, what are the actual executables that come together from the many different instruments that are pulling together data from the outside, that are being mapped to the high-performance computer, and that are intended to show the visualization, again based on software on the system, that is going to be used by the scientists in making their assessment. All of those pieces are coming together from many disparate places in many versions. If you don't get the version control right, then you are not going to be able to replicate that experiment. And that's an important aha. Science is now very much dependent on things such as version control and understanding just as much as the data in many cases, because the way that one analyzes the software, the way that one inculcates the data into the machine learning, particularly being the lingua franca of the day, is really necessary for replicating things. And then if you look at that, that creates some additional challenges. Our code writers now are unlike the ones that I worked with primarily, again, about a decade ago, the last time I was in the lab systems, in that they were more focused on how do we get an algorithm to run accurately on big iron and how we could get the data all in one place fast enough to make the challenge work. Now it's a lot about how do you combine all of those different people and platforms and have the collaboration work correctly. So the software itself is a collaboration tied to the instrumentation. And so it's really a very different thing. You could almost talk about software physical. I know that's not as catchy as cyber physical, but that is really a thing now. And your software physical systems had best be in order. Second thing I want to highlight. From a security perspective, this software is what comes together in the moment to execute. Thinking about some of the other programs in my backyard is really critical. It makes the assurance problem far harder because it's not simply enough to do the hard work that we've been looking at for a long time in this profession of how do you pull components, disparate components, some untrusted, into one place and gain some assurance. You do not know what you have in the moment. It may have been patched live, and you don't necessarily know who is sharing. So that piece has really changed the game. I'm hearing it's about time. I'm just going to squeeze in, transition to Michael Quaid. Thank you.
Thank you. Thank you for those great insights, Deb. I'm going to remember software physical systems. Next, we'll have the opportunity to hear from Dr. Michael Quaid. So as the Vice President for Research at CMU and co-chair of the Defense Innovation Board Science and Technology Subcommittee, can you please describe the challenges you see in bringing research to practice and discuss ways that we could bridge this gap, including strategic partnerships with industry, government, academia, and research labs? And Michael, I ask this question because as we think about the future of software engineering, we'll need to think about how to enable strategic partnerships and collaborations to drive innovation in our broader ecosystem.
Great. Thanks, Anita. And since I'm the one on the agenda with a CMU tag under my name, let me also thank the other panelists for joining us. And for all of you, welcome to CMU, if only virtually. So great set of questions. Let me ground it by taking a step up for just a second. First of all, I will tell you that I never lose an opportunity to espouse the virtue and unique competitive position this country created over the last 100 years of this amazing triumvirate of frontline universities doing basic research, often sponsored and paid for by the government laboratories who do a combination of fundamental research and directed research, and a country that has an extraordinary component of private sector companies that are not just doing research to get the next product out the door, but are doing research for the long term. That triumvirate has created the world we live in today. As an aside, we should not be surprised when our competitors try and replicate that model, and that's a competitive world we live in. But take that for just a moment, because I want to make the point that software, and maybe by analogy, AI and other things, can often change that model. In a world where particle physics which is where I grew up, particle physics was always done at a national lab or a university, and private sector companies would then use the benefit of that research to turn it into commercial products. Things like software, things like AI, the research is as much done in the private sector as it is done in academia or the government. That means we need to think differently about how we bridge the gap between research and commercialization. The second thing I would say is that software and related fields oftentimes these days have a much shorter clock cycle associated with how rapidly things go from research to implementation. And in many cases, we have the opportunity to try by doing, which is a different model than what you might do at a particle accelerator. So keeping all those things in mind, our world is changing and we need to be aware of that. Our traditional models for how we transition technology to the market are different than they were. What do we need to think about from an action? First of all, it is vitally important that those people working in our research fields understand the potential applications of what they do. So when we think about programs of exchange and transitions and rotations, we are very, very immature in that. Our ability to move people in and out of government, our ability to move in and out of academia and in and out of industry needs to change. So point number one. Point number two, we have to educate leadership in each of those three environments much more vigorously on what technology might do. We never want to be in a situation where somebody says, oh, just go get me some of that AI and I will solve all my problems, whether that's a battlefield problem or a product problem. So educating decision makers on the what technology might do is critical. And third, I would just put a very strong marker down for programs like the NSF I-Corps program, which are fundamentally about teaching people who want to transition research what that really means. What does it mean to talk to users? What does it mean to have users talk to you? What does it mean to have people embed with you? What does it mean to really understand how I can evaluate a potential market or a potential product in that market? Additional thing I would say is we need to get the balance on the research side right. There are two answers at the extremes, which are extraordinarily situationally dependent. Neither answer is generally right. So one answer is I have a challenge, let me fund research to meet that challenge. The other extreme is I have some technology, let me work on it, and then we can figure out what it's good for. They both have a place. They are not general solutions to the problem. So constantly thinking about where we need to be on that continuum, I think, is extraordinarily important. And then finally, I would just reiterate what I said before, making sure that our researchers have a much stronger connection to what the application might be. I'll bow to Bill's catechism of if I'm 100% successful, so what? But we need to be thinking about that from our research from the very beginning. What can it do if it can do what it said it was going to do? And with that, I think Vint is up next.
That's awesome. Thank you, Michael, for those great considerations. As we start putting all these various ideas together about the ecosystem and the different roles and responsibilities, you really gave us some great considerations. Thank you. So next we'll have the opportunity to hear from Dr. Vince Cerf. So Vint, you're known as the father of the internet for the design of the TCP IP protocols and the architecture of the internet. TCP IP offer just enough constraint for standardization and just enough freedom to foster proliferation. What's the equivalent from your perspective of TCP IP for engineering large-scale software-enabled socio-technical ecosystems?
And tell me all about the universe in 25 words or less. Okay, it's a great question. First of all, let's warn the audience to distinguish between vision and hallucination, and these need to be carefully, assessed. And second, I'm not going to lose an opportunity to urge SEI to work really, really hard on bug prevention and discovery, software to help avoid making stupid mistakes that later can be exploited by the bad guys. We are not good at this yet, and I look to SEI to really work hard on that. But to answer your question specifically, I would start with the notion of minimum viable product. What's the least that you can get away with to satisfy the most important of your requirements? Second, anticipate iteration, both to satisfy additional requirements you've already identified, but also to discover later, as things are in use, new functionality that might be needed. This is sort of like people say, how do you sculpt things? And the sculptor says, I chip away everything that isn't the sculpture, and then I end up with what I want. One thing which is very important in design is getting to the right level of abstraction. If you're too low a level, things get very confused very, very quickly. If it's too high a level, the model isn't very helpful. So adjusting the level of abstraction for design purposes is very, very important. And then you want to analyze the design for its opportunities for expansion. In the case of the internet, it's a layered architecture. The layers of protocols have very well defined and have had very stable interfaces between the layers. You can add more protocols in any particular horizontal layer, and that has happened. For example, HTTP came along and introduced the World Wide Web, thanks to Tim Berners-Lee and his colleagues. And that was a layer of protocol on top of TCP IP, for example. So many protocols have been added at new layers, and many of them have been added in horizontally. You want to make sure your design has this kind of expandability. I want to also reinforce what Deb was saying about version control. That's super important when you're dealing with software. And her notion of just-in-time software which sort of meets at a certain point in time is vital in a network environment where every time two machines interact with each other, it may be an experiment that's never been done before. And we need to be aware of the fact that things are not necessarily all locked down in these kinds of environments. So in the last point, I think, is that the application programming interfaces and the libraries that serve them are vital parts of today's software world. And it's important to maintain those libraries and to make sure that they are safe and secure and are bug-free. And I can tell you that running off to source code does not necessarily guarantee you bug-freeness. In fact, if anything, since everybody's in charge, nobody's in charge. And so we should be very cautious about using open source libraries and to double check to make sure that they are, in fact, as secure and safe as we want them and need them to be. So I'll stop there and look forward to some discussion with the attendees at the end of this session.
That's great. Thank you, Vint. We very much appreciated your points and your perspectives. Next, we'll have the opportunity to hear from Mr. Alan Dynec, who's here for Mr. Tim Dare. So in your roles with OSD R&E, you have responsibility for a range of software and system engineering activities. And so as you think about the future of how software will be developed, what is the grand challenge in rapidly developing and deploying software-reliant systems based on user intent versus only on user requirements?
Thanks, Anita, and thanks for the opportunity to speak, and certainly thanks to SEI for putting this together. Within DoD, a focus is obviously operational systems that have some critical functions. And so we're very concerned about getting behaviors and trusting them with behaviors that can in some cases be fairly significant. So one of the things that we would want to make sure we understood is certainly how you capture intent. What do you mean when you say, I want to have intent? We need a sort of a stable set of semantics that allows us to communicate. We understand that in our operational environment, there are many units, entities that have very different ways of communicating similar information. And so what we want to do is first of all, make sure that we can define the method by which we would translate that intent. Certainly we understand as imperfect as it is the current development environment. We understand some of its limitations and in terms of being able to go faster and sort of not being stuck in some ways with a waterfall heritage where we're trying to move much more quickly and deploy software that is resilient and more responsive to operational needs. So, but understanding the semantics by which we would be able to capture that intent moving forward. But a major impediment, I think, in any of these systems, and not to steal anyone else's thunder, but to jump on, is really the data problem. In any system that we're trying to leverage, particularly things like AI machine learning, we have a tremendous data gap in our environment. Acquisition of systems very often leads to data stovepipes and data that's basically parked behind very difficult firewalls, and that's a quantity of data that would be necessary. Really a need for a sort of a unification, but not only of data, metadata, but really kind of a meta semantics. What does the data mean? And the same format, the same type of data may look and appear very different to different parts of DoD in their operational environment. And in some cases, some data requires a cultural context. How do I interpret this? Say a call for a certain type of action. In some environments, that requires a concurrence or an authorization. In other environments, it simply is the request will be fulfilled unless there's a denial. How do we capture that kind of information so that the systems will do what they're intended to do with a consistent set of expectations? And of course, when you start to look across information security, we have a unique problem in DoD in that we not only have at the top level security management and usage management and what's appropriate to do and how it's appropriate to use our data, but also data aggregation. When data comes together and we may very quickly get to a place where we have to really understand how that data is going to be controlled so that we don't have spillage of information that's very sensitive. So all of those things are going to be critical. And then operations, when we talk about intent of systems, and operating in a contested environment, we assume that future environments are going to be denied. Many of the things that we've come to rely on in our information systems and our command and control systems are going to be denied. So how do those systems continue to operate with various kinds of degradations that may be very difficult to predict? How do we make sure that the intent of the system to operate continues to operate even when there's a lack of communication or there's sudden lack of positioning data or other kinds of things? So those are some of the areas that we think would strongly impact that and would be a concern going forward.
Great. Thank you, Mr. Dynec. We really appreciate your points. Those are great considerations. Next, we'll hear from Ms. Sarah Manning-Dawson. So we can't discuss grand challenges or grand opportunities without focusing on the primacy of data. Alan Dynec just brought up some of the data issues. So in your work in engineering the hyperscale cloud, what advances are you working on that will enable the kinds of data use, protection, and integrity that are a necessity for any advancement of software engineering?
Yeah, thank you, Anita, for the opportunity to be here and to share a little from my experience at Microsoft. I think the term data primacy here is interesting because people often think of data in terms of the stateful data, right? The stuff that lives for a while sitting on disk. And really, data is at the center of everything we do in cloud computing. You know, it's what the compute environment is acting on and reasoning over through processor and memory. It's what we send over the wire or over the air, and it's what we store on disk. So, you know, when I think about the journey of where we've been and where we're going in the hyperscale cloud, particularly in the context of use, protection, and integrity of the data, I think we face some unique challenges around how to operate the cloud while engineering our services to ensure the confidentiality and integrity of that data and, you know, the users of it. So I would say probably the biggest two innovations or advances in service of these challenges is number one, confidential computing, and number two, what I'll describe as the increasingly distributed computing environment that we call cloud, but that really exists across endpoints and users, edge, and the hyperscale cloud. So to delve a little further into confidential computing, you know, imagine you're an organization or a company, you've had a compute environment on your premises for a long time, whether it's in your basement with your IT staff or you've got a local data center, and you make a decision to move to the cloud. You know, especially in the earlier days of cloud services, there was understandably a lot of angst around losing control of that environment. Because by definition, right, moving to the cloud means moving your environment, the operations, and the management to someone else, somewhere else. And, you know, it was very important for both cloud service providers like us or Amazon or Google to, you know, be able to let cloud users know that no one would touch their stuff, right? And for these cloud users to know that too. And so, of course, we started with sort of well-understood security goodness, like offering strong encryption on disk and over the wire. But our users want to know that even when the data is in use, so the data in memory is kept private, you know, they want to know that if operators have admin access to the machine or the operators are physically present in the computing environment, the data is still held confidentially. And so confidential computing, which is tethered to a hardware-based root of trust and not the software of the cloud provider, completes that promise across the full computing environment, including data in memory. So not just data at rest, not just data in transit, but data in use. And we're seeing this technology being offered in all of the major hyperscale cloud providers, which I believe is good for our cloud users and good for the promises around data confidentiality. The second thing I mentioned is this increasingly distributed computing environment. And this one we're really in the early stages of, but it is pretty exciting because it sort of changes the definition of the hyperscale cloud, right? It's an incredibly powerful and scalable processing environment. But as cloud computing broadens its reach and moves deeper into digital environments beyond traditional IT, like to power substations or oil platforms, we're encountering unique needs to have options to process some things on location, whether it's because of network isolation, intermittent or costly connectivity, data sovereignty needs, or extreme low latency needs. And so what we're seeing is that in response, cloud providers are creating smaller and smaller scale data center form factors. So think of these as micro data centers that we can deliver to a power substation or a military base or an oil platform, and it really blurs the lines between the hyperscale cloud and the edge. So we're also seeing this being offered by major hyperscale cloud providers as well, and really excited about this road ahead. Thank you.
That's awesome. Excellent insights, Sarah. And I see that within our panelists, there's some comments and on confidential computing. So we'll come back to that at the end of our session. But thank you. So next we'll have an opportunity to hear from Dr. Bill Shurlis. So Bill, the question that I've thought about for you is, at DARPA, you lead program managers in the development of research, technologies, and advanced capabilities to ensure information advantage for the United States. How extensively does information advantage overlap with software engineering advantage? And what are the primary software-related areas you feel will lead us to advantages in both realms?
Thank you, Anita. That's a very broad question. I'll just try to touch on some of the key points. I'm going to start with three general points about why we do what we do. And the first is that the information domains that you mentioned almost entirely manifest their capability through software. As we all know, software is everywhere. There's more of it than before. It's in more significant roles. It's the favored building material in the military sense, both the non-kinetic and the kinetic domains. A second general point is that, and this is very important, our software practice stays creative. And what I mean by this is the engineering of software, that practice will not be routinized, although we must struggle continuously to make it so. And this is a kind of a conundrum, and this conundrum exists because with software, we're unshackled by the laws of physics, and so the abstraction level continues to go up without bound. And this means that we're able to connect more closely with our domains. That's the pull. But it also means we're never going to fully automate software construction. A third general point I want to make is that software is the enabler for nimble engineering. This came up earlier, Vince remarks, and several others as well. This idea, which at DARPA we call it the pipeline, is a broadly expressed aspiration now in the DoD. It's been the standard of practice in the SaaS world, in the commercial sector for decades. But in our world, there are formidable challenges to manifesting it. And the idea is to blur prototyping, development, and sustainment, where sustainment for software is really evolution. It can start with an MVP, minimal viable product, as Vint pointed out, but it does not always start with traditional requirements, but rather a sense of the scope and mission and the intent, the general area of intent. It's also designed from the outset for integration and interoperation. Whenever you hear somebody from the government talk about an interoperability problem, you know that it's not a technical challenge. It is always a challenge of business models and incentives and the will to engage. The pipeline models have become an imperative for three reasons. One is that the threat environment that we face now is nimble and capable. Both peers and non-peers can pivot rapidly. We have to be able to do the same. We can't go with the model, we used to call it the requirements delay surprise model, where years go by and then you get something that turns out not to fit the need. The second driver is the technology advance. Obviously, everybody's talking about AI, but there are a whole range of other technologies that also are being brought to bear. And then the third is the consequent fluidity of mission concepts with hybrid domains, modern battle management, and the like. So I've got a minute left. I'll mention some areas of research. I've got actually 4 broad areas, and within each about 3 or 4 particular technical areas. So I'll just mention the 4 broad areas. in each of these areas, the 13 particular challenges and all that I was going to mention, there are DARPA programs in all those areas. So if you want to connect with those, please reach out. The first is what I'll call software-enabled complex capabilities. For example, how do we engineer systems that embody AI and machine learning capabilities? Generally, when we're talking about AI, we're talking about not just machine learning, but hybridizations with game theory, knowledge representation, search and planning. And so we have to think about how to build trustworthy systems from these inherently right now flaky components. But it also includes, for example, IoT and CPS. The second broad area are what I'll call software structures, architecture, human system symbiosis, performance technologies, data engineering, security engineering. Third broad area, software engineering models, analyses, and evidence, formal methods at scale. For example, engineering traceability and evidence, program understanding. And then the fourth area is software engineering activities and infrastructure, test and evaluation, continuous ATO, authority to operate, tools, data. Software engineering is a very data-intensive business now, and all that data manifests evidence that we can then apply, and then also, of course, model-based approaches. So my fundamental final point is we have to stay focused on advancing our software capability. We also have to figure out how to adapt our business models to make these things work. Thanks very much.
Thank you. Always eloquent, Bill. Thank you very, very much for all of your insights. And now our final speaker, before we get to some questions and comments, Mr. Nan Mulch. So the DoD considers AI to be one of the keys to national security. What are the key AI engineering challenges that must be solved so that AI can live up to this promise?
Thanks, Anita. And let me see if I can sum up all of AI in the military in 4 minutes here. So one of the fun parts of working at the DoD around AI is that everybody immediately jumps to their favorite disaster movie involving robots. So it's either Terminator and Skynet. And I think the way to think about this is that people are thinking of artificial general intelligence as being applied to all these problems. So the big question is, I personally don't know what it's going to take to get AGI out of the realm of science fiction into reality, but there's a lot that can be achieved along that axis. And so let me see if I can articulate some of this in a structured way. So when we think of applying AI and the software engineering challenge of bringing AI into the military, I typically have been starting to call this software-defined warfare, in some sense, sort of pulling from what we've done in data centers in industry and others. And some other people call it things like military Internet of Things. But regardless of what you call it, there's sort of two big things that we think about in this area. And the first is what we think of as autonomy, which is, think of at the tactical edge a set of autonomous, reconfigurable hardware systems that's really focused on human-machine teaming, sort of in a local way. So think of special operations, think of the unit level of things happening on the ground. And the second A is automation or orchestration, which is really, a lot of people think of this as swarming, or other types of algorithms, but basically pulling all of the back-end information together, both from a, logistics, intelligence, readiness, blue and red force tracking, et cetera, all of this pulled together and moving it from the intel side to the ops side. And this is really the focus of what we're thinking of when we talk about missions like JADC2, which is Joint All-Domain Command and Control, or ABMS, which are the Advanced Battle Management System projects going on at the DoD. So you've got the local piece, which is autonomy, and then you've got the automation piece, which is really about connecting all of these things together. So that's really generally how I think about the problem, sort of in a very simplistic way. So let me now move to the sort of software engineering challenge side of this. And I break this up into what I think of as the supply side and the demand side. And on the supply side, you really have, obviously, industry, academia, CMU, obviously, great research institutions doing a huge amount of work on advancing the state of AI. And in there, you've really got what I think of as an x-axis and a y-axis. So on the x-axis, really you're thinking of narrow AI, which is a set of building blocks or domains that we can apply different algorithms and different techniques to, such as image recognition or NLP or full motion video object detection. So these are on the x-axis. And then on the y-axis, you've got the AGI axis, which is really about starting with things like predictions and reasoning, and then moving your way up maybe to infinity, where you get to things like AGI and truly sort of human thinking, which is generally what most people think of as there. Now, the good news is on the narrow AI side, the x-axis, we are making a lot of progress. There's certain domains and areas where we read about in the news, some computer system beats some champion in some area, or the AI system is able to play Pong really well. So, however, in the military, as you can imagine, we're dealing in the world of physical hardware. We're dealing a lot with vision. We're dealing a lot with the tactical edge in a denied and degraded environment. So even at the outer edge of the x-axis, we're dealing with technologies that are not really scaled. So things like Project Maven, for instance, you may have heard of, around full motion video object detection, still very, very hard. The really bad news is that on the y-axis, around reasoning and things like pattern of life and other things, we're still very, very early on. And so the idea around being able to assemble and reason around these objects is still very limited. And the last thing that I'll end with is, so there's a supply side of that where we're, I think, still in the sort of lower, sort of lower part of the quadrant, if you may, when it comes to the supply side. And then on the demand side, the DoD just needs to do a better job of being able to integrate and receive this technology. So first thing is architecture. One of the points is AI is living software. There's an entire loop of being able to develop and deploy AI software continuously. Trust in the system around explainability, data issues, and these are all problems that we still need to do. So if I were to sum this up, the supply side is getting better, but the demand side itself requires a huge amount of work, which is probably where the biggest software engineering challenge lies. Thank you very much.
Great. Thank you, Nan, for those incredibly insightful comments. You gave us a lot to think about in terms of the supply and the demand side. So we have, what I'd like to do is, before we take questions from the audience, I would like to ask the panelists if they would like to comment on what they heard their fellow colleagues talk about, or even ask a question or two to their colleagues. And we've had this chat window going, so I know, Vint, you'd like to maybe kick off just a few comments, and you wanted to reinforce the idea of confidential computing, something that Sarah talked about.
Yes, thank you so much for giving me that opportunity. Sarah, you and I are both, I think, equally excited about confidential computing. It just adds a whole other dimension to protecting customers' information and their software in a way that isolates them not only from everyone who is sharing the cloud, but also with the organization that's offering the cloud. And in our case, of course, it's at Google. In your case, it's at Azure. So I just want to reinforce that that's a game changer, I think, for a lot of people who would otherwise be reluctant to commit resources and their company's assets to cloud-based computing. The second thing I wanted to bring up has to do with open source. There was a comment about it in the chat. And I would say that if we think of open source as a gift horse, then make sure you look it in the mouth carefully. As opposed to not doing so. I would see open source as a wonderful opportunity to get access to software, but at no time should you make assumptions about its safety or security, particularly given what was said about the idea of just-in-time coalitions of software interacting with each other that Deb brought up.
Awesome. Thank you, Vint. Deb, I know you wanted to comment on this idea of nimble engineering that Bill had talked about. So, Deb, I'll open the floor up to you for a minute or two. Oh, Deb, you're on. Yeah.
There you go. So thank you. And I'm hoping Bill will dive in as well. So Also want to foot stop. Confidential computing is going to be absolutely critical for science, especially as social scientists, because we need to have a way to effectively work with that data without revealing individual components. So that's a must-have in my view, and we really need to be investing more on that from the scientific side as well as the military side. Open source, agree entirely as well. Gift horse. It's always running with us. But the nibble engineering I wanted to hit, partly because I think this is another must-have, but I'd like Bill to talk a bit more about the safety issues involved. We must have it because we need to have a way for collaborations to come together quickly around a problem. COVID was a great example. There was a great deal of excellent work done in order to pull different software models, essentially, looking at the analytics, looking at potential for vaccine. It happened without the time for the normal checks and balances. How far can we go and how far should we trust the nibble engineering, I'm wondering, and Bill, I know you've thought a lot about that, so perhaps you could take a little time and go further.
Thanks, Deb. This is a really significant topic for us at DARPA. We're looking at nimble or pipeline models in two respects. One is as a means to support the transition of technologies from the lab into practice, into the supply chain. This was a point that got raised very early by Michael. We implement that model, for example, with respect to cyber capabilities, and as Nan knows, we're working with the JAIC with respect to emerging AI capabilities. These are fast-moving areas. We have fast-moving threat environment. Fast-moving thinking on what the mission capabilities ought to be. We have to have the nimbleness. So that's one aspect of our engagement. But the other aspect of our engagement is in developing engineering, tooling, technological foundations, scientific foundations, mathematical foundations to enable nimble practices that address the challenge that Deb pointed out, which is how do we get to high levels of assurance for these fast-moving systems. Most people in the software world are familiar with the Ariane 5 story from the European Space Agency many years back. That's a story about an engineering team that did not want to go through the gate of authority to operate, and so they kept the old software that they knew was broken. And so the costs and uncertainties of these evaluation gates are a significant impediment. So our focus here is on the accumulation and management of this large body of evidence. I pointed out earlier that software engineering is a data-intensive activity. We have models, we have analyses, we have test cases, we have the code base, we have the full history of the code base. If we can build formal structures around this evidence, argumentation structures, safety cases, hazard analyses, all the various things, the models that engineers are familiar with, then we can actually use our tooling to have all this evidence fly in formation in a way that we can predict the outcomes of these evaluation gates. This is very much an emergent phenomenon in the safety critical community. But if you look at the very best commercial practices, since Google and Microsoft are with us, there are two great examples of this. We see a lot of these ideas showing up in these practices. So the idea of evidence flying information is one key thing. Secondary is the architectures, the way we organize the components of our systems into aggregate capabilities. We have to think about architectures in a way that we get for incremental effort, we get incremental improvements in capability, and then incremental activity to recertify those systems. So that notion of incrementality is key. That's enabled by architectures. Think about the framework and apps on your mobile device, but also the way web apps are constructed, for example, the NPM ecosystem, or even the old-fashioned big data with Hadoop and its family. In the military context, former Chief of Naval Operations, Admiral Greenert, talked about platform and payload with respect to the engineering of systems. These ideas are fundamentally significant, the architecture. And then the third piece of it, the three A's, assurance, architecture. The third A is activity, or you think of it as agility. It's the practice, the process of following the agile ideas. The only way you get to agile at scale is with architecture. Otherwise, you can't scale up beyond the 6 people in the room. So you put those 3 pieces together, you get something that works. Now, the Defense Science Board, Paul Nielsen, the director of the SEI, was a co-leader of that activity a year and a half ago. The Defense Innovation Board, Mike McQuaid, was part of that process. Both of these groups have made recommendations that tilt very strongly in this direction. So I think this is really an important capability for us to develop.
Great. Thank you so much, Bill. Sarah, I know you had a question for Nan. That'll be maybe our last question amongst our panelists, and then I'd like to take a few questions from our audience. But Sarah, I know you had a question for Nan.
Yes, thanks, Anita. And pardon the light. I'm in Seattle, and it's the first time in 2 months that light has come in this room. So I can't complain, but I know it might be strange.
Solar therapy.
Yeah, I'll take it. Nan, you had described the x-axis and the y-axis, x being some of the current AI tech, and then the y sounded like a description of how it sort of ups its game to become more and more sophisticated. And I was just interested in your thoughts on which aspects of those x-axis items you feel are climbing the fastest, and what does the near-term future look like?
Well, thank you. Well, I mean, I think the news reports glow a lot on the sort of left hand of the x-axis, right? You've got things like NLP and image recognition, et cetera. Any kind of bounded problems where sort of you can apply huge amounts of compute or the algorithms are skilled, et cetera, I think are doing incredibly well. The place where we're starting to struggle is, as I said earlier, where we're moving to the right on the x-axis in terms of UAV, full motion video object detection, right? Huge problem just in the basics of being able to identify objects, different lighting structures, different sensor technologies, and that too in the mode of adversarial AI, right? Where if the data gets leaked, if the algorithms are well known, et cetera, there's easy way to spoof these highly bounded algorithms that can perform very well with good training data sets that are bounded and algorithms that are, I call this looking for the keys under the light, which is once you've bounded the problem, you can do a great job of extensively doing something there. But anytime you go outside of it, the explainability, the ability to predict and control that, especially from a commander's perspective when they're throwing, people and you're doing targeting and a number of other things that are very, very tricky to do. And also you want to do them incredibly well and with discretion, becomes incredibly hard. And then on the y-axis, once you have the building blocks there, you can identify what we call dots on a map, say, the ability to reason about them. So just take the idea of tracking 2 cars on a road. Are they moving together? Are they together? Are they trying to overtake each other? Is one trying to crash into the other? Are they driving on the right side of the road? We can't even make basic, just even from the current tech, the ability to reason off of dots on a map itself is incredibly hard. A aircraft getting refueled at a base, for instance, what does that mean? Where are they going? What are they going to be doing? Where are they deploying to? So anyways, huge unanswered questions. So, however, the last thing I'll say there is even though we're there is this aspect of we're really behind, what typically happens is things are slow. There's some breakthroughs and inflection points, and all of a sudden, something that we had envisioned that would take 20 years all of a sudden appears out of nowhere. So anyways, thank you for the question. It's great.
Yeah.
Thank you.
That was a great question, Sarah, and I really appreciated your response on that. Michael, I wondered if you could comment on the Defense Innovation Board study, Software is Never Done, because there were several questions in the chat about what that really means. And so I thought maybe you could really comment on that.
Great. So thank. Let me make just 2 comments on what it is and 1 comment on what it is not. And as always in this circumstance, it's always good to have smarter people already make the point. So we specifically chose Software is Never Done as the title of that report to accentuate 2 things. 1, Vin talked about this before. You simply don't do software by requiring it, writing it, testing it, and then rolling it out to the field. That is simply not the way any sane and rational person or organization does software. And that was important for us because it led to a series of recommendations about how you fund software. So if you don't do software that way, funding software by saying, write all your requirements, then we'll write a contract for you to develop software. To prove to us it's all right, then we'll write a contract to deploy software. So software is never done means software is an evolving capability that you roll out and improve. Bill made the second point, which is software is never done, is also a statement that software is not a physically constrained object. And while the physical instantiation of the compute may constrain you, or the comms may constrain you, or the sensors may constrain you, the software does not constrain you. And looking at how software can evolve to meet mission needs is another reason we use that term. What it does not mean, and we don't stress this enough, it doesn't mean you do crappy code. It doesn't mean you write software and it's okay if it's not any good because we can fix it later. That is precisely not the intention of software is never done. I stress that because anybody on this call, anybody listening in who ever has to go argue a program to a funding agency, anybody who has to argue a program in front of a House staffer or a senator, please don't say software is never done because we never get it right.
Great. Thank you. Thank you. Okay, I'm going to we only have 10 minutes left, and there are so many questions. So let me see if I can get to a couple of them. And Alan, there's a specific question I'd like you to address. I have that teed up too, but first from Patty. It's directed to you, Nan. Do the DoD trade-off technology decisions limit us from achieving the transition to AI? That is, not all domains or infrastructures are equal in data, infrastructure, or operational use.
Yeah, that's a tough question. Let me see if I can answer this quickly. The way to think about it is when you're evaluating investments, there's sort of two ways of thinking about this. I think of this as the vitamin versus the painkiller problem. And what tends to happen is the headache or the toothache typically gets the money first, right? It's one of those things where you can recast a project one way or the other. And in many cases, a great example is logistics, right? Not the hottest, most exciting thing. You're not going to get a science fiction movie about logistics. That's a blockbuster, billion-dollar blockbuster. But as they say, amateurs study tactics, experts study logistics, right, in the military. And so it's one of these things where the hottest thing gets the investment and the tech, while the sort of more important stuff typically languishes. So I think the audience member asked that is right on, that typically sometimes we won't make the right trade-offs. But applying good business practices and thinking about how to do investments with return on investment, et cetera, is something that I think we need to obviously do a better job in the government. But it's just like any other large enterprise where, there are all kinds of trade-offs, whether it be tech trade-offs or business trade-offs or politics. These all things come in. So the answer is yes, they do limit us, but we're obviously always striving to try to do a better job of that. Thank you.
Thank you. Thank you, Nan. Alan, I thought you could at least start by fielding this one. It's a workforce question. What actions need to be taken to ensure that the U.S. has the workforce talent to take advantage of the opportunities for this software-enabled future? So I think that's something that you and Mr. Dare and other folks in OSD R&E are thinking very critically about.
Oh, so give me an easy question. So I think that is, there are a lot of challenges there. I think structurally, and here's where I try not to get fired, structurally within the government, it can be difficult to find and retain folks. In my experience doing software commercially and as a contractor, very often we change jobs because we wanted to go on to the next cool technology, right? We wanted to move on. It really wasn't so much about money. Money helped. So how do we keep those, how do we create that environment within our own space, within the government, so we have people who are challenged, they're moving from effort to effort. I think there's a part of the job that's really based in mission. So when you're participating in mission, that's an additional call beyond the technical part of it. But I think a lot of it really has to be, maybe some partnerships, internships. We've been working with a couple of organizations, one funded study to look at this, and also the software workforce group internally. And there's been a lot of discussion about doing this. And there's not going to be one bullet, because software commercially is moving very quickly. In the government, I think we tend to try to, let me have an Ox series, and let me categorize this in this way, and then you're going to have this progression, and the system tends to favor seniority over skill. And so what we need to do is really think about, the appropriate distribution. What kinds of things should we contract for, right? The kinds of skills, the kind of activities it's better and more efficient. And what kinds of things do we really need to own inside? And how do we make technology available so that our very smart warfighters can actually take that technology and apply it in a mission-relevant way? So hopefully that wasn't too long or off topic.
No, that's
over.
No, thank you, Alan. Thank you for those insights. I know that's a pretty broad question, but I just wanted to, I know this is something all of you OSDRNE is thinking about critically, so thanks for those comments. There's a question from Donna for Dr. Franke. As we move forward with quantum computing, how do you see AI aiding and helping to rewrite algorithms from the existing HPC software and weapons codes for modeling and sim?
Great question, and that's one that a lot of people are very enthusiastic about. I have to put in my little bit of a plug. Really, the quantum sensors are a thing we can think about nearer term. We've got the ability to build those now and so on. And when we talk about quantum helping in this context, we are likely talking about high-performance quantum, at least possibly medium, high, intermediate, but more likely high performance that's bracketed between two classical systems. So you're probably looking at something like that. But in that context, there are many people trying to seek out whether the architectures tied to a qubit-based motion and the ways that you can compute with very large numbers of quantum might be more appropriate for some of the advanced simulation and modeling needed in that area. One that I'm especially interested in is fallout, because that is really complex when you've got to get weather conditions, direction. There are just a lot of interesting things that need to be looked at. A hesitation that one must have when you're looking at the weapons codes, especially it's tied to very sensitive data and models that are used and calibrated versus using classical methodologies. And so you can't simply move to a new model. You might have different outcomes. There needs to be some way to correlate the results you get from a classical approach. Again, the software being part of the sensor, you've changed sensors in essence when you change models. We'll go to quantum. So that would be a caveat, but a lot of people looking at using something like this when it becomes available.
Great. All right. And possibly this is the last question. It depends how quickly we can get through it. And it's from Tom Longstaff, our CTO. So to avoid fighting the last war, how do we define and embrace a new way of looking at vulnerabilities, bugs, and defects in increasingly complex and emergent systems? I don't know.
Are you looking for somebody to respond to that?
Sure. Would you like to kick it off?
Well, just a short one, and that is to pay much more attention to trying to model what it is that software is trying to do. Modeling and testing of models is probably better than trying to build a theorem that says the program does what it's supposed to do, because we've broken our pick on that. But models are very valuable in my view, and also looking for invariants that could be tested for an operational piece of software and as another tactic. None of these solve the entire problem, but paying a lot more attention to it would be helpful.
I'll build on that. That's incredibly important for working in the large. There's also an in the small that needs to be considered. So in the moment execution is the bringing together of all those disparate pieces. Adversaries can, for the next war, certainly become adept at pulling together small components of executables. They already are, in terms of stringing together and making their own code running live based on what's already on the system. So the ecosystem is part of the issue. So if you can combine Vince's description of what we need to do in the large with an additional focus in the small, you've got a good breadth. I would caution us from thinking we can forget the last war. Unfortunately, the last war is always available to the adversary due to legacy systems.
I pile on one last comment, which is that there are many models that we must use. They are proliferating. That's good. Each model lets us focus on one aspect of the system that we care about independently of the other aspects. The more the better. And the reason the more the better is that what we do not model is what we do not understand. And from a security perspective, a side channel is a channel that relates to some aspect of the system behavior that is not modeled.
Great.
And one more pile-on just to give you some, just one more thing to think about as you think about what crazy things will happen 25 years from now. One of the things we talked about confidential computing, and sometimes we talk about secure computing. I actually worry, to Deb's point, when I have small executable capability, I actually worry about the day when an adversary goes into battle without compute, but just absconds compute from what's available in the battlefield.
Yes, great. I am going to ask one more question. Alan, I'm hoping maybe you could take a shot at it, but really anyone, and this will be our last question, and it's on systems engineering, and I think that's another really important perspective for all of us to keep in mind. It's from Ranjiv. What are your thoughts on how systems engineering could provide a holistic perspective on the relationships between AI, fusion, human adversaries, context, etc., on software engineering?
Okay, another easy question.
I know.
So I'll start off with saying when I was a software engineer, and I learned from some very good people about software engineering, and when I switched to system engineering, I realized this is just good software engineering practice. It's something that simply has to expand, right? System engineering was making, from my perspective, various kinds of software work across multiple platforms that included different types of hardware and different types of software embedded capabilities. And I think as you're expanding, the one thing you can't do with it is make system engineering the thing that slows everything down. Because one of the knocks that I've heard on system engineering is, I can't afford 6 months to do requirements. Well, that's not a good evolution of systems engineering. What really has to happen is that process has to continue to evolve to provide its conceptual benefit without adding time, right? And whatever time you take for it, it has to contribute to the ultimate quality integration of the approach. So I think it's an important thing not to forget system engineering in the rush to move forward,
right.
But we can't let it stretch out. Over.
Thank you. Well, I guess we really are out of time, but please let me end this session by thanking all of you wonderful visionaries, your enthusiastic participation, the way that you think about and frame some of software engineering's key open problems, considerations, visions, and the grand challenges. And of course, I want to thank all the attendees for all of your engaging wonderful questions. So thank you all. And I think that we're going to take a very short break before we return back to the research review. So thank you all.